Okay, so let me share my screen. And okay, so we're finished with chapter. Oh, before I forget, you may have noticed that I've posted your scores for your first assignment. I'm going to send back the graded work to you later on this evening so that you can have that review. I'm also going to post the answer keys online so you can compare, what you have to what the answer key says. And if you have any questions, if you think I've made an error in grading something or adding up the points or whatever, please feel free to contact me about that, all right? Okay, so we're moving on to chapter 3, which deals with, again, another topic which you should have covered in your introductory or high school chemistry. And that has to do with stoichiometry. And stoichiometry, as you may recall, or maybe if you weren't told, is that area in chemistry which deals with the quantitative relationships between substances involved in a reaction, all right? So if you have a reaction that you have a balanced equation for, then if you know this, for example, if you know the amount of reactants that you are given to use to cause the reaction, then you can calculate how much product you expect to get. Or vice versa. If you want to get if you want to get a certain amount of products, you can work backwards to determine how much reactants you're going to need in order to get that much product. All right. So that's basically what stoichiometry is all about. And this is a very fundamental skill that you need to master so that you can do some other stuff in chemistry, including up to organic chemistry. All right. So let me talk about firstly molecular masses and formula masses. Very fundamental thing that you need to be aware of, which you should know already. So that's why I'm going to go through this rather quickly. So simply put, the molecular mass is the sum of the atomic masses of the atoms represented in a molecular formula, right? Very simple, all right? Now, this term molecular mass is specifically for molecules. When it comes to other compounds, ionic compounds especially, because they don't exist as molecules, there's an alternative term known as a formula mass, right? And it's pretty much the same thing. The only difference is that we add up the atomic masses according to the formula unit, right? As opposed to the molecular formula in the case of molar mass or molecular mass, all right? But it's basically the same thing in terms of the units, especially. The units would be atomic mass unit in either case, all right? So just to give an example, if you're asked to calculate the formula mass for ammonium sulfate, the first thing you're going to need is the formula for ammonium sulfate, right? And in this case here, the formula for ammonium sulfate is NH4 2SO4, right? So what you'd have to do now is look up the atomic mass for nitrogen, which is 14.01 AMU. But because of this 2 here, you have to multiply by 2. Or in fact, you know what? Let me do it this way. What I'm going to do is add 14.01 to 4 times 1.008 AMU for the hydrogens, for the 4 hydrogens. And then I'm going to multiply all of that by 4. I think that's a bit easier to work with. And then I'm going to add to that the atomic mass of sulfur, which is 32.0, is it 6? 32.06? Can somebody tell me? Because I can't see it from here. For sulfur.
And 32.066.
Oh, okay, 0.06. Okay, so AMU. And then for oxygen, there are 4 of them. So 4 times 16.00 AMU. All right, so that's basically how that is set up. So let me work this out. So it's 4 times 1.008 plus 14.01. And then I'm going to multiply all of that by 4. And then I'm going to add to that 32.06. And then I'm going to add to that 4 times 16. And according to my calculation, and please correct me if I'm wrong, all right? But I got 168.23 AMU. And that's it. And that's basically how you go about calculating the formula mass of a compound. All right? So obviously, you're going to need a formula, which means that if you're given a name of the compound, then you have to determine what the formula is. And we already know how to do that based on what we did in the previous chapter. Okay, any questions about this? Any questions? Yes, ma'am.
We should multiply it by 2, I think.
Multiply what by 2?
Not the 4 in the front, because it's NH4 and bracket 2.
Oh, you're right. You're right. Thank you. Thank you. This should be 2, so I need to redo this. Thank you very much, Miss Patel. Okay, what's going on here? So let me redo this again. 14.01 plus 4 times 1.008. And then I multiply by 2, not 4. And then I add 32.06. And then I'm going to add to that 4 times 16. Okay, so the answer is 132.14. You got that? Okay, good. Thank you, Ms. Patel, for correcting me on that one. All right. Okay, so that's basically how you determine the formula mass of an ionic compound. All right. Another concept that you should have encountered in your previous chemistry experience is the concept of the mole. The way I explain the mole in chemistry is I like to use the term dozen. We all know what the term dozen means in everyday language, right? Everybody knows that it doesn't mean 12, right? So the mole is kind of like a similar counting unit, right? Excepting that it's a very huge number, right? And that's because in chemistry, of course, we're concerned with particles like molecules and ions and so on. And usually, if you have a small amount, if you have, let's say, 1 gram of something that has billions of atoms or molecules, whatever. So therefore, we need a large counting unit to deal with those kind of situations, right? So basically, here's the definition of the mole. The amount of substance that contain as many elementary entities as there are atoms in exactly 12 grams of the carbon-12 isotope. So that's the actual definition of the mole. Now, in terms of the number of items, elementary entities, particles, and so on, that's in a mole. That's a big number, as I said before, and it's equal to 6.022 times 10 to the 23, right? So that represents the number of items in 1 mole of literally anything, but we do apply it, as I said before, to small particles, ions, atoms, and so on, right? So 1 mole of, let's say, hydrogen molecules contain 6.022 times 10 to the 23 hydrogen molecules, all right? And so on and so forth. Okay, so as I said before, that term mole can literally apply to anything. And as stated here, 1 mole of oranges, let's say, would weigh about as much as the Earth, just to give you an idea as to how large a number that is, all right? Now, one key thing you need to do whenever you're doing calculations and so on, is that when you're abbreviating the mole, you do not use the letter, any of the letter M's, uppercase or lowercase. At best, the only abbreviation that you should use is MOL, right? But you cannot use lowercase m or uppercase m because those two symbolisms mean different things and they certainly don't mean more, right? Lowercase m would be meters, for example. Uppercase m, which we're going to meet later on, is molar or mole per liter, right? We're going to meet that later on, all right? Okay, so just to expand on our understanding of this whole mole concept, let's look at this simple reaction. The reaction between carbon and oxygen to form carbon dioxide. So that is represented by these spheres here, right? So you can clearly see it's a 1-to-1-to-1 ratio in terms of the atoms and molecules present. If you expand this to 12, 1 dozen, that means that 12 carbon atoms will react with 12 oxygen molecules to form 12 carbon dioxide molecules. And if you extend that to 1 mole, which of course is 6.022 times 10 to the 23 in terms of the carbon atoms, then that will react with 1 mole of oxygen to form 1 mole of carbon dioxide. All right? So basically, if you're given a balanced equation, that balanced equation does not only tell you what happened at the atomic or ionic or molecular level. You can expand it to the molar level, so to speak, in terms of the moles of the different substances. And you're going to see how that will help you in terms of making the type of calculation that is common in stoichiometry, where, as I said before at the start of the class, you can start off with a certain amount of reactants and determine by calculation how much of a product you expect to get, right? And this also shows you that the conservation of mass law is obeyed, because 1 mole of carbon atoms has this mass, 1 mole of oxygen atoms has this mass, and 1 mole of carbon dioxide has this mass. So basically what you're going to see is that the total mass of the carbon dioxide produced will be equal to the masses of the oxygen and the carbon that is added together, all right? So basically what this indicates or shows is that the mass is not created or destroyed as you go from the reactants to the products, which is basically what the law of conservation of mass is saying. Okay, so this brings us now, oh, I thought I was going to get to molar mass. Anyway, very important that you recognize that 1 mole of different substances will have different masses, right? And that is demonstrated in this example here. So here we have 1 mole of sulfur, 1 mole of copper, 1 mole of mercury, and 1 mole of helium gas, right? If you were to weigh these, you're going to see that they all have different masses, all right? So basically, it's important that you recognize that 1 mole of different substances will have different masses when you weigh them in grams or pounds or whatever, right? So this brings us now to the concept of molar mass, right? The molar mass, by definition, is the mass of 1 mole of a substance, right? And it turns out that numerically speaking, the molar mass would be the same for the atomic mass when it comes to elements, the molecular mass when it comes to molecular compounds, and the formula mass when it comes to ionic compounds, all right? The difference is the units, right? So numerically, they're the same, but the units will be different. Whereas, in the case of molar mass, the units would be expressed in grams per mole, but in the case of atomic mass, molecular mass, or formula mass, the units will be expressed in AMU as we saw earlier, right? So numerically, they're going to be the same, but the units are going to be different. So just to give you some examples, the atomic mass of sodium is 22.99 atomic mass units, but the molar mass of sodium will be 22.99 grams per mole. Numerically the same, but the units are different, all right? I think I have another example here. 1 molecule of carbon dioxide, its atomic mass, its molecular mass, I should say, is 44.01 AMU, but its molar mass is 44.01 grams per mole. Again, numerically the same, but the units are different. And I think I have one more example lined up here. Yeah, this is an example of an ionic compound where the formula mass is 74.56 AMU, but the molar mass is 74.56 grams per mole, right? So therefore, molar mass and formula mass, atomic mass, molecular mass, same numerically, but the units will be different. Okay, so as a result of what I've just discussed, right, we can establish relationships between the mole of a substance, the number of elementary particles in that substance, and the molar mass of the substance. And an example is shown here. 1 mole of sodium will contain this much atoms. Oh, by the way, I think, did I tell you what, hold on, let me see here. Maybe I skipped over it. I skipped over it, right. So this number here is known as Avogadro's number. Let me highlight it here. So this number, the 6.022 times 10 to the 23 is known as Avogadro's number, all right? So that's the number of particles or entities present in 1 mole of that, whatever, all right? So, yeah, I should have mentioned that earlier. So let me go back to, okay, so this is Avogadro's number, which relates directly to the mole of the substance and also relates to the mass in 1 mole of the substance, which is the molar mass, right? So as a result of that relationship, or those relationship between those three items, we can establish conversion factors between any two, right? And it all depends on the type of question that you're asked, right? So you can write down, for example, a conversion factor which relates the mole of a substance to its molar mass, as shown here. So this is one way of expressing it. Another way of expressing it would be here, right? In other words, you flip this to get this. Which one you use is dependent on, what you're trying to achieve. It depends on the question that you're asked. And then you have this example here where you have a conversion factor which represents the relationship between the mole unit and the molar mass, right? And you can have other conversion factors which represents, for example, the relationship between the number of sodium atoms and the mass of sodium atoms. So it all depends on what you're asked to do. And also, in addition, again, depending on the type of problem, there may be some preliminary questions or preliminary setups that you'd have to do to get to a certain stage, and then you use that conversion factor, and then you may be asked to do some other calculations based on that. So again, it all depends on how the question is worded. Now, based on the formulas of different compounds, you can actually establish the mole relationship between each element in the compound and the moles of the actual compound, all right? And that is demonstrated in this example. So here we have a molecule where the formula is C3H8O3, right? So based on the formula here, well, firstly, okay, let me just say this first. Based on the formula here, you can say that, okay, one molecule of this compound will contain 3 carbon atoms, 8 hydrogen atoms, and 3 oxygen atoms. So that's one way of looking at it. But there's another way of looking at it in terms of the mole, in terms of the moles of the original compound. You can say that 1 mole of this compound contains 3 moles of carbon, 8 moles of hydrogen, and 3 moles of oxygen, which is what is shown here, right? So again, it depends on the type of question you're given, because there are some questions, and I think there's one question in the assignment I'm about to give you, where you're going to utilize this idea where there's a mole relationship between the mole of the substance and the moles of the individual elements within the substance based on the formula, right? So you're going to see that in one of the problems, if I remember correctly, when you do assignment number, was it 3? Okay, and then over here we have another example. This time it's an added compound, and this time you have to be careful because you have an NH4 unit that is doubled right here, right? So this 2 here would multiply the mole value of nitrogen by 2. So you're going to get 2 moles of nitrogen here. And as far as the hydrogen is concerned, 2 times 4, 8 moles of hydrogen. So that's why you end up with 2 moles of nitrogen here, 8 moles of hydrogen here, and then the rest is straightforward, right? So basically 1 mole of that compound will contain these mole values for the separate elements in that compound. So again, as I said before, you might find that approach useful when it comes to solving certain problems. Okay, all right, so here we have an example, which is actually 4 questions in one example. So the question says, determine A, the mass of a 0.0750 mole sample of sodium, B, the number of moles of sodium in a 62.5 gram sample, C, the mass of a sample of sodium containing 1.00 times 10 to the 25 sodium atoms, and D, the mass of a single sodium atom. All right, so I think I'm going to do this here. Oops, sorry. What I'm going to do is move this up a bit to create more space below. Okay. All right. So let's do the first part. It's asking for the mass of a 0.0750 mole of sample of sodium. So what I would do is start off with, this is A. I hate red ink. Okay, so for A, we're going to start off with what we're given, which is 0.0750 moles of sodium. So the question is, what would be the conversion factor which would allow you to convert from moles of sodium to the mass in grams, right? And that would be the molar mass, right? So what you'd have to do is consult the periodic table. And if you look at the periodic table, you see that sodium has a molar mass of 22.99 grams per mole, right? So that would be 22.99 grams of sodium, which would be the numerator, and then 1 mole of sodium downstairs, which would be in the denominator. So let's do the calculation here. So that's 0.0750 multiplied by 22.99. And according to, let me do this again, 0.0750 multiplied by 22.99. Okay, so according to my calculation, this works out, now in this case, I have to round up to 3 sig figs. So I got 1.72 grams of sodium. All right, and that's it. All right, so that's the A part, relatively simple. The B part is basically asking for you to do the reverse. The numbers will be a bit different, but it's a reverse process, right? Because in the case of the B part, they're asking for the moles and they give you the grams. So you start off with what you're given, which is the grams of sodium. And this time, you're going to multiply by a conversion factor, which would be the flipping, which would result from the flipping of this here. In other words, 1 mole of sodium would go above, and 22.99 grams of sodium would go below. All right? So let's see what that gives. 62.5 divided by 22.99. And according to my calculation, I got rounded out to 2 sig figs, 2.72 moles of sodium. And that's because this grams of sodium will cancel out with that grams, and that's how that works out. All right? Any questions about this one? Any questions? Any questions? Okay, in the case of the C part, they gave you the number of sodium atoms, and they're asking for the mass. All right? Now, this one will be slightly more complicated because you might not be able to, unless you're exceptionally brilliant, you might not be able to go directly from atoms to the mass, right? But what you can do is start off with the number of atoms, right? And then convert that to moles. Now, how would you do that? Well, if you remember, we said that Avogadro's number represents the number of particles present in 1 mole, right? So the way we can represent that here in this conversion factor is that we put 6.02 times 10 to the 23 sodium atoms as the denominator. And above, you're going to put 1 mole of sodium, right? So the sodium atom units will disappear, will cancel out. So you're going to end up with mole of sodium as the unit up to this point. But of course, we can't stop there because the question is not asking for the moles of sodium, it's asking for the mass. So that's where the molar mass comes in. And the way we represent that here in this conversion factor is that we put 22.99 grams of sodium above as the numerator and 1 mole of sodium below. And then that goes with that. So therefore, your final answer will be expressed in grams of sodium. So let's do the number crunching. 1 times 10 to the 25 divided by 6.02 times 10 to the 23 times 22.99. And according to my calculation, when rounded off to 3 sig figs, the answer is 382 grams of sodium. And that's how that works out. All right? Any questions about that one? Any questions? No questions? Okay, now let's look at the D part. I'm going to need some space. So let me erase the first line here. And maybe the second line. Now, in the case of the D part, they're asking for the mass of a single sodium atom. Now, basically, this can be done because we know what the molar mass represents, right? That would be the mass in grams of 1 mole of a substance. And we know that 1 mole contains Avogadro's number of atoms of that substance, right? So basically, to find the mass, this is the C part, to find the mass of a single atom, all we have to do is take the molar mass, which is 22.99 grams per mole, right? And divided by Avogadro's number of atoms, which would be 6.02 times 10 to the 23 atoms per mole. All right? So the mole units will cancel out here and here. So you're going to end up with grams per atom, I should say, right? Which is what the question is asking for, right? So all we have to do is divide the 22.99 by 6.02 times 10 to the 23. And according to my calculation, I got rounded off to 3 sig figs, 3.82 times 10 to the minus 23 grams per atom. And that's how you do that. All right? Okay, any questions about that one? Any questions? Okay. Tell you what, let's get started on assignment 3. This is for you. All right. So for now, what I want you to do is focus on questions. Oh, and by the way, how could I forget? For the person out there in Zoom, let me publish it in Canvas for you. Okay, so this is assignment 3. All right, so Addison, you should now be able to download assignment 3. I've just published it. All right. So what I want you guys to do is focus on question 1. Question 1. All right. Let me help you with the first one, and then you can do the others on your own. So the question is asking for you to complete the following conversions. And in this case, for the first one, you're going from grams of water, which is 0.00515 grams of H2O, and they're asking for you to convert it to moles, right? So my question to you is, what do you think you should multiply the given mass in grams? What should be the conversion factor that you multiply that by? In other words, what would be the numerator and what would be the denominator in this conversion factor right here? What should go up top? Water. 1 mole of H2O. And what should go below? Well, specifically, the molar mass of water. So what you have to do is go to the periodic table and you look up the molar masses of hydrogen and oxygen. And if you do that, you're going to end up with the molar mass being 18.02 grams of H2O. All right? And then you do the number crunching. So that's 0.00515 divided by 18.02. And according to my calculation, I got 2.86 times 10 to the minus 4 moles of H2O. All right? So that's how you do that. All right, so you should be able to do the others. So, but if you have any questions, of course, please feel free to ask. All right? Okay, are we finished or almost finished? All right, let me give you 2 more minutes and then we move on to some other stuff. Okay, somebody's asking for part B, would I need to multiply my answer from 3.5? Yes. So this person is asking if after multiplying 3.5 by 6.02 times 10 to the 3, 10 to the 23, which of course is Avogadro's number, then you have to multiply by 3 because if you look at the formula, there are 3 atoms, sodium, oxygen, and hydrogen. The way I would do this is I would start off with 3.50 moles of sodium hydroxide. And then, as she correctly said, multiply that by 6.02 times 10 to the 23. I would put formula units for every 1 mole of sodium hydroxide. And then I'd multiply this by 3 atoms over 1 formula unit. And that would give you the answer, which is okay, so the answer I got is 6.32 times 10 to the 24 atoms. Let me do this again just to make sure I'm doing the right thing. 3.5 times 6.02 times 10 to the 23 times 3, right, 6.32 times 10 to the 24 atoms is what I got. Yes, sir.
Look at multiply the atom first and then multiply by the 6.0.
I'm sorry, repeat that?
Look at do flip flop, do the atom first and then do the multiply by the 6.022 times 10 over 23.
So you're saying multiply 3.50 by 3?
And then
Yeah, it would make a difference. In fact, another way of setting it up would be 3.50 moles of sodium hydroxide. And you could do this. For every 1 mole of sodium hydroxide, you have 3 moles of atoms. And then you multiply this by 1 mole of atoms. And Avogadro's number 6.02 times 10 to the 23 atoms. And you're going to get the same result. So that's an alternative way of setting it up. All right. Okay. Let me clear this here and go back to the PowerPoint. And let's move on to a discussion of percent composition. I alluded to this concept earlier, but we're going to get into it in more detail, right? And again, this is one of those topics you should have encountered in your previous chemistry experience. So usually when we're talking about the percent composition of a substance, we're referring to the mass percentage composition, right? And it's very simple. Basically, you take the mass of the particular element and divide it by the mass of the entire compound, multiply by 100%, and that represents the percentage of that element in that compound, right? So there are a couple of ways this can be done. You can take the mass of the element in 100 grams of the compound, take that divided by the 100, and that gives you the percentage of the element, or you can take the mass of the element divided by the mass of the compound times 100%, and that gives you the percentage of the element that is present in the compound, right? So it's relatively easy to calculate the percent composition of pretty much any compound if you know the formula, right? So just to illustrate that, how we do this, we're gonna use butane as an example. So the formula for butane is given, C4H10, right? So basically to find, well, firstly we find the molar mass, I hate red ink. We find the molar mass of the entire compound first, right? So molar, okay. So the molar mass of C4H10, again, we just go to the periodic table and we look at the molar masses of the different elements. So in the case of carbon, that's 4 times 12.01 grams per mole. And then we add that to 10 times 1.008 grams per mole, right? And let's see what that gives. So okay, so according to my calculation, this works out to be equal to 58.12 grams per mole, all right? So to get the percentage of carbon, we take this total mass of the carbon, which is 4 times 12.01 grams per mole, and divided by the total molar mass, which is 58.12 grams per mole, times 100%. So let's see what that gives. 4 times 12.01 divided by 58.12 times 100. So according to my calculation, this works out to be equal to 82.66. 82.66%. And then I do a similar calculation in the case of hydrogen. 10 times 1.008 grams per mole. Take that and divide it by, again, the same molar mass, 58.12 grams per mole. And then I multiply that by 100%. So that would be 10 times 1.008 divided by 58.12 times 100. And I got 17.34%. And of course, when you add these two together, you should get 100%, which is indeed the case. All right. So that's basically it, right? Very simple concept. You just take the mass of the individual element and divide it by the total molar mass of the entire compound. All right. So that's how you calculate the percent composition. Okay, let me see here. All right, let's look at these examples. Let me move this up again to create some space below. Okay, so the first example says calculate in 4 significant digits the mass percent of each element in ammonium nitrate. So of course you need to figure out what the formula for ammonium nitrate is. And the formula for ammonium nitrate is NH4NO3. All right. So to find the percentage of each of them, first you have to find the molar mass of ammonium nitrate. All right. So that would be, okay, so in the case of nitrogen, that's 40.01 grams per mole, plus 4 times the molar mass of hydrogen, which is 1.008 grams per mole. And then I add to that another nitrogen, which is 14.01 grams per mole. And then I add to that 3 times 16.00 grams per mole. So let's see what that gives. Okay, so according to my calculation, this works out to be equal to 80.05 grams per mole. All right. So to find the percentage of nitrogen, that would be 2 times 14.01 grams per mole divided by 80.05 grams per mole times 100%. Right? So 2 times 14.01 divided by 80.05 times 100. So according to my calculation, this works out to be 35.00%. And then we have a similar calculation for what's the next element? Hydrogen. So that would be 4 times 1.008 grams per mole divided by 80.05 grams per mole times 100%. So that would be 4 times 1.008 divided by 80.05 times 100. And according to my calculation, this works out to be 5.037%. And then we do finally the percentage of oxygen, which is 3 times 16.00 grams per mole divided by 80.05 grams per mole times 100%. So 3 times 16 divided by 80.05 times 100%. So this gives 59.96%. All right. And I would check to make sure that everything adds up to 100. So let me do that now. 35 plus 5.037 plus 59.96. Right. I didn't get exactly 100%. I got 99.997 when you add them up. So that's approximately 100%. All right. So that's how we answer the first question. Now the second question is asking how many grams of nitrogen are present in 46.34 grams of ammonium nitrate. Now, in order to answer that question, we're going to need this answer right here that we got for the first part, because that gives you the percentage of nitrogen in the compound, right? So all we have to do, let me just erase top part here. All we have to do in order to answer that is take the 46.34 grams of ammonium nitrate that is given, and we multiply it by this percentage, right? So the way I would express that percentage is that I would put 35.00 grams of nitrogen above, and below I'm going to put 100 grams of ammonium nitrate below. And that's it. So 46.34. So according to my calculation, this works out to be equal to 16.22 grams of nitrogen. And that's how that is done. Okay, any questions about that one? Any questions? Okay, so now what we have done is relatively easy. That is getting the percent composition from the formulas. The reverse is a bit more challenging, all right? In other words, if you're given the percent composition of a particular compound, how can you determine the molecular formula, right? Well, it's a bit more difficult to do that, but there are some steps involved which I'm going to go through. The first of which is that basically we express the percentage for each element, if you're given that data, you express the percentage as if it represents the mass in 100 grams, right? So in other words, we assume that we're working with 100 grams of the compound. And if you assume that, that means that each percentage represents the mass in grams for every 100 grams of the compound, all right? And then what we do next is we convert each of those masses to moles. How do we do that? We divide the mass in grams by their respective molar mass of the different elements. Then what we do next is find what is called the whole number ratio. And the way we do that is that once we determine the moles of each element, we divide right through each of them by the lowest mole value, and that will give you hopefully the whole number ratio. But you might not get the whole number ratio at that point. And then it becomes a bit more complicated, because if you get something like a fraction, then the next step would be that you'd have to multiply everything by a certain number that would convert that fraction into an integer, all right? So those are the steps involved. Once you get those numbers, then you get the empirical formula, and then from there you can get the molecular formula with additional information. So the best way to learn this is to go through an example, and we have two examples right here. Okay, so let me do this. Let me get out of this here. All right, let me create a new slide. And let me go back up. Oops. And let me copy this here and paste it on the next slide. And let me go back to the previous one. Let me take this out. Let me, okay. I hope I have enough space down here to do what I plan to do. All right, so this is the first question, which gives you some data, percentage data, for a compound known as phenol, right? So I'm going to go through the steps using this particular example. So if you remember, I said, the first step is that we assume that we are working with 100 grams of the compound, right? So basically what that means is that we can express these values as grams, right? Because these are the mass in grams for every 100 grams of the compound. Now, what I like to do when I'm doing these problems is I like to set it up in a tabular fashion. I'm going to set up a table here. So at the head or the top of this table, I'm going to write down carbon, hydrogen, and oxygen, right? And the first row will be the mass values. So as we said before, we're assuming 100 grams of the compound. So therefore, each of these numbers here, I'm going to express in grams. So for the carbon, that is 76.57 grams. For the hydrogen, that is 6.43 grams. And for the oxygen, that will be 17.00 grams. All right, so that's the first step. The second step is where we convert each of these mass values to moles. So as I said before, to do that, we have to divide each of them by their respective molar masses. So in the case of carbon, that would be 76.57 grams. And what I would do is multiply this by 1 mole over 12.01 grams, right? So if I do that, 76.57 divided by 12.01. So according to my calculation, this works out to be equal to 6.376 moles, all right? And then I do a similar calculation in the case of hydrogen, 1 mole over 1.008 grams. So let's see what this gives. And according to my calculation, this works out to be 6.38 moles. And then in the case of oxygen, 17.00 grams, I'll multiply that by 1 mole over 16.00 grams. So that would be 17 divided by 16. So I got 1.063 moles, all right? So that's this step, convert the grams of each of them to moles. The next step is where we find the simplest ratio. And the way we do that is that we look at these three numbers here, this one, and this one. And we choose the one that is lowest, which is this one, and we divide all of these by the lowest. So in this row here, we're going to divide right through by 1.063 moles, right? So here I'm going to put 6.376 moles divided by 1.063 moles. I'm going to do the same thing here, 6.38 moles divided by 1.063 moles. And this divided by itself will give you 1. So I'm just going to put 1 right there. So let's work out these two. So 6.376 divided by 1.063. So this gives 5.998. And then for the next one is 6.38 divided by 1.063. And this gives 6.00, right? So you'll notice that this number here is very close to 6. So we can simply approximate that to be equal to 6. This would be 6, and that would be 1. So therefore, the empirical formula, let me squeeze it down here. The empirical formula, which is what the question is asking for. The question is asking for the empirical formula. The empirical formula is going to be equal to C6H6O. So these numbers, the 6 and the 6 and the 1 here, will be the subscripts in the empirical formula. And that's basically how that is done. All right? Any questions about this? Any questions? Any questions? Any questions? Okay, let's look at the next example. Similar question, we gave you the percentage data, and they're asking for you to do the, to determine the empirical formula. So again, I like to set it up in a tabular fashion. The first row will be the masses, where I express the percentage values in grams. So for carbon, that is 45.27 grams. For hydrogen, 9.50 grams. For oxygen, that is 45.23 grams. And then we find the moles. So to find the moles, we divide each of them by their respective molar masses. So 45.27 grams. I'm going to multiply that by 1 mole over 12.01 grams. Hydrogen, 9.50 grams. I'm going to multiply that by 1 mole over 1.008 grams. And then finally, in the case of oxygen, is 45.23 grams multiplied by 1 mole over 16.00 grams. All right? So let's work out what each of these would give, starting with the carbon, 45.27 divided by the 45.27 divided by 12.01. And when I did that, I got 0.08. No, that can't be right. That can't be right. Let me do this again. 45.27 divided by 12.01. Okay, I don't know what I was doing to get that crazy result. Okay, so this is 3.769 moles, all right? And then in the case of hydrogen, 9.5 divided by 1.008. So in this case here, I got 9.42 moles. And then in the case of oxygen, it's 45.23 divided by 16, and that gives 2.827, all right? Okay, so the next step, if you remember from the previous example, what we do is that we examine each of these mole values and choose the one that's lowest and divide right through by that value, right? Which would be the 2.827. So I'm going to put here divide by 2.827. 27 moles. So 3.769 moles divided by 2.827 moles. Let's see what that gives. So 3.769 divided by 2.827. Okay, so in this case here, I got 1.333 no units because the mole units cancel out. Okay, and then 9.42 moles divided by 2.827 moles. Let's see what that gives. 9.42 divided by 2.827. And in this case, I got, 3.33. And then finally, in the case of, well, this one divided by itself will give you 1, all right? So this is the result when we divide each of these by the lowest mole value. Now, you'll notice in the case of these two results, this one and this one, those numbers are not anywhere near an integer, right? If you remember, when we got to the stage in the previous example, one was what? 5.99, right? Which is very close to 6. So in that case, we just round up to 6, right? But we can't do that in this case, all right? What we have to do is that we have to multiply right through by a certain integer, which brings these numbers close to an integer, right? So in this case here, I can tell that if I multiply everything by 3, right, then the 1.33 times 3 will give 3.999, which is very close to 4, right? And then in the case of the next one, 3.33 times 3, that gives you 9.999, which is very close to 10. And because we multiply the previous 2 by 3, we have to multiply the 1 by 3, so that gives you 3. So therefore, let me just squeeze it up here. The empirical formula in this case is going to be equal to C 4 H10 O3. And that's it. All right. So there are some instances where when you get to this stage right here, you cannot simply round up or round down the number because that number is too far from the nearest integer. You have to choose a number that you'll multiply those numbers by that will convert it to a number which is closer to an integer, right? And in some cases, you can tell what you multiply by because I could tell, for example, that if you have a recurring 3 after the decimal point at this stage, you just multiply by 3, right? If you have a 5 after the decimal point, you multiply by 2. If you have anything 0.25, you multiply by 4. Anything 0.75, you multiply by 4. If you have a recurring 1 after the decimal point, you multiply by 9. And what else? If you have a recurring 6 after the decimal point, you multiply by 3. And those are the ones that come readily to my mind right now. In other cases, and I think that's the case in one of the questions that you're about to do in the assignment, it's simply a trial and error thing. You have to try different numbers to see how you convert these numbers into the nearest integer. Okay, any questions about this? Any questions? Any questions? All right. So before we move on to the next question in your assignment, there's one more thing I need to talk about. So basically the examples that we looked at so far, you're given the percentage data, right? And you're asked to determine the empirical formula. But what if you're asked for the molecular formula? Well, in that particular instance, you're going to need an additional piece of information. And the information that you're going to need will be the molar mass, right? So basically, if you get the molar mass of the compound, what you can do is divide that molar mass by what is called the empirical formula mass, right? The empirical formula mass is basically the same thing as the molar mass, excepting that you apply it to the empirical formula, right? So basically, if you divide the molar mass by the empirical mass, then that will give you an integer, right? And that integer you can multiply the empirical formula by to get the molecular formula, all right? So I think I have an example here. In this example, they gave us the empirical formula for this compound, hydroquinone, C3H3O. And it gives you the molar mass or the molecular mass as 110 AMU, right? So the question is asking for the molecular formula. Let me move this up further. Okay. So basically, we need to find empirical mass. So the empirical mass is based on the empirical formula, which is given right here, right? So that would be 3 times 12.01 AMU plus 3 times 1.008 AMU plus 16.00 AMU. All right? So let's see what that gives. So that's 12.01 times 3 plus 3 times 1.008 plus 16. Okay, so according to my calculation, this works out to be equal to 55.05 AMU. All right? So if I were to divide the molar mass or molecular mass by the empirical mass, that would give you a ratio which should be an integer. In some textbooks, they call it the integral factor, right? Symbolized by the letter I. So basically, I'm going to take the molar mass, which is 110 AMU, and divide it by the empirical mass, which is 55.05 AMU. So let's see what that gives. 110 divided by 55.05. So that gives 1.9. I'm sorry. If I roll out to 2 sig figs, that would be 2.0, right? Which would be 2. It should be an integer, right? So therefore, the molecular formula is going to be C3H3O, and you multiply that by 2 to give the final answer, which is C6H6O2. And that's basically how you do that, right? So you could be given a question where you're asked to determine the empirical formula, like in the 2 previous examples that we just did, and then you could be asked further to determine the molecular formula, in which case you're going to need the molar mass, and then you just go through the steps, divide the molar mass by the empirical mass. That should give you an integer, and then you multiply the empirical formula by that integer, and that will give you the molecular formula. Okay, any questions about this example? Any questions? Any questions? All right. Okay, so now you should be able to do, let me see here. Okay, so number 2, which is relatively easy. So I want you to do number 2. Number 2 is just asking for you to determine the percent composition of each element. So, you know, you add them up and then you divide each of the elements, molar masses, by the total molar mass. So that's number 2. And then number 3 is an example or questions like the examples that we just did. You're given a percentage data and you're asked to determine the empirical formula. Let me just look further down. All right, so 3, A, B, C, you should be able to do. Okay, right, so those are the questions I want you guys to focus on right now. Questions 2 and 3. And if you have any questions, of course, please feel free to ask, all right? I'll be right back.
I just. I'm going to about find what my permission wants to look. What he wants it to. What did you guys get for the first part? See.
Because C 12, page 12 into 03.
Oh, no, for number two, the percentages.
No? I got it wrong, I did 5 and yeah, and so,
And then yours all round to like 103.013. I added all of mine up, yeah, but it's still fine, because it's still.
yeah, on this one. Yeah,
I
on
didn't.
this one, I didn't do the mistake on this one, so. So,
Okay, those are too much.
Okay, I just want to make sure,
Yeah.
and I don't even know where to start being, to be honest, I'm just gonna do that at home.
This one,
Yeah.
all you gotta do for this one is for no and when would you be two, H would just be two, and then C will be one and O will be one.
Yeah.
So you do that.
But what will the numbers for the moles, the gram per mole, do I have to look that up on? Is that?
You have to find what each of these are.
Mhm.
And then once you do that, you just divide,
You divide the total number.
Same thing with this, you have to find each with the C. No, C is 12.01 to 016.
Mhm.
N, I believe, come on,
Cause I don't know what N is, and I feel.
N is 12.01.
12.01, okay, yeah, no, I didn't know what that was, and on my notes, for some reason, I have it on here where when I had N, I had 14.01, and then I just did plus, I didn't really multiply it by anything. Oh, wait, but never mind, because N is multiplied by 1.
Bro, I feel like we get a homework every day, bro.
I thought, I was confused when we got the homework for today, because on Canvas, we don't even have an assignment in for assignment number 3, or we didn't even go over everything for assignment number 2.
no, but, yeah, it's not the best, it's not, it was just.
Okay. Um. Have you gone to question 3A yet?
Mhm.
Or are you finished with it?
Mhm.
Oh, okay, all right, tell you what, so. You can do the rest of question 3 later on, because I want to get to, what time is it, by the way?
11:40.
Wow, okay, hold on. Let me see. All right, and the rest of the time that we have here, I'm going to talk about elemental analysis. We may not be able to get, let me see here. Okay, yeah, we may not be able to get to the example that I was hoping to get to for that particular topic, but let me just start off by talking about elemental analysis. So some of the questions, including the one that I just showed you, they gave you the data, the percentage of each element present, right? What we're going to look at is, in one particular instance, how do we get this data, all right? And we have to conduct an experiment known as elemental analysis, which basically gives you the amount of each element present in a given mass of the substance. Now, this method I'm about to get into specifically applies to organic compounds. And when I say organic compounds, I'm talking about compounds of carbon, right? These compounds typically contain carbon, hydrogen, maybe oxygen, and maybe some other elements like nitrogen, halogens, and so on, right? But carbon and hydrogen are usually the main constituents of these compounds, right? And the reason why this method works best is because it's based on burning the organic compound. And whenever an organic compound is burnt completely, 2 products are always produced: carbon dioxide and water, right? So basically the carbon in the original compound will end up in the carbon dioxide. the hydrogen in the original compound will end up in the water, right? So if you can somehow trap and weigh the carbon dioxide that's produced and the water that is produced, then based on those masses, you can work backwards to determine the mass of the carbon and the mass of the hydrogen. And then based on other information, you can get the mass of the other elements if they're present, right? So as stated here, carbon dioxide and water would be the normal products of the combustion of these organic compounds. So if you can trap them and weigh them, then you can determine the mass of the elements present in your original compound. So this here that I'm showing you on the screen is a schematic representation of the combustion analysis experiment, right? So I'm just going to describe quickly what is involved here. As you can see, there are three separate compartments, right? So the first compartment will contain the compound that you're analyzing, right? So what you would do if you're actually doing this experiment is that you would weigh the compound first and make sure that you record it, right? And then you place it here. Now this compartment here is playing the role of a furnace. So therefore there'll be some heating element in there which would burn the compound, right? Oxygen will be forced into it because you need oxygen to burn it, right? So you burn it, and then all of it is burned and forming carbon dioxide and water, which is led into the second compartment. Now, in the second compartment, you're going to have a substance which will absorb the water, right? And magnesium perchlorate is the substance that is used in this case. There's another substance which can be used, which I don't remember right now. But anyway, magnesium perchlorate is a substance that will be used in this case to absorb the water that is produced. So again, if you were doing this experiment, what you'd have to do is that you'd have to weigh the magnesium perchlorate first before you start the experiment. And then as you put it in the compartment, and then as it absorbs water, basically the mass of the magnesium perchlorate would increase, right? So the difference between the initial mass of the magnesium perchlorate and the mass after the absorption of water would give you the mass of the water that is produced, right? So the assumption, of course, is that you have enough magnesium perchlorate here to absorb all the water that is produced from the combustion of your sample, right? So if that's the case, then the only thing that would emerge from this compartment would be carbon dioxide, right? And that would be led into this compartment, which will contain a substance which will absorb it, right? In this case, it's sodium hydroxide. You can also use potassium hydroxide for that same purpose, right? And again, just as in this case here, what you'd have to do is weigh the potassium or sodium hydroxide that you use before you start the experiment. And then upon completion of the experiment, when it absorbs the carbon dioxide, you're going to get the mass increase, which would be the mass of the carbon dioxide that is produced, right? So basically, as a result of this experiment, if it is done correctly and everything, you're going to end up with the mass of the carbon dioxide and the mass of the water that is produced from a given mass of the original compound, right? So as stated here, the sample is burnt in oxygen, and then the next compartment is where the water is absorbed by the magnesium perchlorate, all right? And then here is where carbon dioxide is absorbed by the sodium hydroxide, all right? And then based on the increase in the mass of water and in the increase in the mass of carbon dioxide, you can determine the mass of carbon and the mass of carbon and hydrogen in the original compound that is being burned, right? And this is just basically a model representation of what I just described. So let's say the compound that you're analyzing is methanol, right? So this would be the reaction that would take place when methanol is burnt. It forms carbon dioxide and water, right? And based on the amount of carbon dioxide and water that is produced, the carbon dioxide would be absorbed by the sodium hydroxide. The water is absorbed by the magnesium perchlorate. So basically, you can figure out, based on the mass of the carbon dioxide, what the mass of carbon that would be present in the original compound. And based on the mass of the water, you can determine the mass of the hydrogen that is present in the original compound, right? And then after that, you'll be able to do some calculations to determine the empirical formula, right? Okay, so I'm going to stop here because this example is a good example of the calculations that you'd have to perform in order to do a combustion analysis problem, all right? So what you should do in the meantime is do questions, well, you said you completed question 3A, right? So do B, C, and next class, we'll get to this question 4 based on the example that we're going to do when we get together next time, all right? Okay, so that's it for today. And I'll see you guys tomorrow. Oh, I see some of you in lab, right? Right, so. How could I forget?
What's your nice?
Yes, sir.
I prefer for lab day, more shorts, but I don't care about apron, do I go something?
Well, we do have some aprons, but you should be fine. Yeah. You should be fine what you're wearing.
Do I have to put my hair up?
Yeah.
I'll see your best, I wanna get that for myself.
I've had only one situation where somebody's here caught on fire. I don't want to repeat that, so. Yeah, make sure your hair is tied up. Even though in this experiment, we won't be using any open flames, come to think of it.
So I have a question. So for chapter 2, we are not doing acids.
Oh, shoot, right, that was the only thing that was left from that chapter.
Yes.
Oh, shoot.
Yeah.
I'm gonna do that first thing next class, tomorrow. Yeah, we didn't get to acids, naming acids.
Yeah, naming acids.
Thanks for reminding me. That's what happens when you're getting old.
For that, the shirt wasn't a problem, right?
Yeah, you're fine, you're fine, yeah.
Professor Nice.
Yes, sir.
Someone left chem homework from student yesterday for.
Somebody left their what?
For their history chem, someone left their homework.
Oh, okay, no problem.
Seeing it now.
Yes, sir. Oh, what am I packing up for? I have another class here. Yeah. Oh, no, I don't.